This video is on section 4.4, derivatives of vector-valued functions. And I'm probably not going to say anything in this video that's going to surprise you. In fact, hopefully everything in this section kind of works the way you expect it to or the way you want to. Remember, I say there are things in math that work the way you want them to. There are things that don't. And maybe there are things here that don't work the way you want them to, but I'm guessing everything that I say here is what you're going to expect me to say. So first of all, the derivative of a vector-valued function, we have the limit as h goes to 0 of f of t plus h minus f of t divided by h, provided the limit exists. Anytime you define something in terms of a limit, you say provided the limit exists. What's nice is Theorem 96. If you define a function in terms of components, and there's nothing magical about 3, it's just that we generally work in V3 and R3 in this class. So f of t is x of t, y of t, z of t. If all three of these functions are differentiable, then f is differentiable and the derivative is what you want it to be. The derivative of f is the vector-valued function whose components are the derivatives of these functions up here. So this is pretty much how you would like to calculate a derivative of a vector-valued function. So for example, if r of t is the vector-valued function sine of t, cosine of t, t squared, the derivative is cosine of t, negative 1 times sine of t, 2t. Now, Theorem 98 is probably also something that works the way that you would like it to work. But we have to be very careful about how we look at these functions. So we start with f and g are functions from r into vn. In the notes I wrote r3 here. I would have rather written v3, but so that should be v3, but really there's nothing special about 3. So up here I'm writing f is a function from r into vn. In your notes it says r3. That's okay. I like vn better. S is a typical real-valued function. So S goes from the reals to the reals. Now, remember from Calc 1, the derivative of the sum is the sum of the derivatives. We liked that in Calc 1, worked the way we wanted it to, and so we had the same thing for vector-valued functions. Remember, this is f of t plus g of t. You add two vectors together, you get a vector. F and g are vector-valued functions. The derivative of the difference is the difference of the derivatives. Just like in Calc 1, when we had real-valued functions, except here we have vector-valued functions. Now, 3, 4, and 5 are all different versions of the product rule, but the formula works very consistent with the product rule that you learned in Calc 1. We just have to be very conscious of whether we're dealing with vector functions or real-valued functions in 3, 4, and 5. So here we have S times F. What is this? Well, S is a real-valued function. So this is a scalar multiple right here. S of t is a number, F of t is a vector, and the way to combine a number with a vector is with the scalar multiple. And then we take the derivative. Now we have something that looks like the product rule from Calc 1, sort of. We have the derivative of the first times the second plus the first times the derivative of the second. What did I mean by times though? I meant the scalar multiple. So we have derivative, scalar multiple. No derivative, the original s, and scalar multiple with the derivative of f. So remember, derivative of the first times the second plus the first times the derivative of the second. All three of these work like that. It's just that we mean something different by the word times. Derivative of the cross product. So we take f of t, which is a vector, g of t, which is a vector, take the cross product of two vectors, which is a vector. Product rule. Derivative of the first times the second plus the first times the derivative of the second. By this time, by times, we mean the cross product. So we take the cross product of two vectors, cross product of two vectors, add those together, and we have a vector. Remember, this is a vector-valued function. 5 by times, we mean the dot product. So to take the derivative of the dot product of f and g, we have f of t, which is a vector, dot g of t is a vector. Remember, dot product's a number. So strangely, this function that we're defining in terms of vectors is actually a real valued function, because a dot product of two vectors is a number. But the formula is similar. Derivative of the first times the second plus the first times the derivative of the second. In this case, by times, we mean the dot product. But we have a real valued function here. We have a real valued function here. So again, this is a little bit odd that we have a real valued function that we're defining in terms of vector valued functions. But keep in mind, this thing is a real valued function. And for part 6, we have a version of the chain rule. F composed with S. What do we mean by that? Well, remember, S is a real valued function. So when you substitute t in for S, you plug t into S, you get a real number. A real number you can plug into a vector valued function, because that's what a vector valued function does. It takes a number and it spits out a vector. So we plug t into S, then we plug S of t into F. So we have a composition of two functions, of a real valued function and a vector valued function. Chain rule. Take the derivative of the outside function, leave the inside function alone, multiply by the derivative of the inside function. What do I mean by multiply? I mean scalar multiple. S of t is a real valued function. So if I substitute a number for S, I get a number. S prime of t is a real valued function. If I substitute a number into S prime, I get a number. So I'm taking the derivative of f. F is a vector valued function. So I'm plugging a number in right here to get a vector. I plug a number in right here to get a number, and this product is the scalar multiple. So everything from Theorem 98 works out in a nice, comfortable way.